So how do you all celebrate Thanksgiving Day today? Have a meetup.
We are thanking to everyone who will join.
It's pretty funny to have here in the United States. I'm sure you're aware of what's going on here. You know, it's strange having a day like Thanksgiving when everybody's at each other's throat. Very an environment with a lot of conflict right now.
Are you democratic state or swing state? Or?
Well, I'm in Pennsylvania, so we are very divided. But I guess we became a democratic state, you know, in this last election. Because we have, you know, in the United States, it basically boils down to the cities versus the rural areas. In particular, the East and West Coast are very Democratic Party, and the less city-like areas are more Republican type of political bent. So it's an interesting challenge here because the country is really divided and it's almost along geographical lines. But you guys know about that. You guys have had a pretty rough few decades.
That's right.
We are set. We can start.
Yeah, you can share your screen.
All right.
With the meetup. Okay. Data Science Serbia has been promoting data science and AI for the past few years. From this year, or more precisely from today, we are launching a new chapter that will promote quantum technologies and their usage or applications. Good evening, everyone, and welcome to the first Quantum Serbia meetup. I'm glad to see that there are so many people who are interested in getting to know more about the quantum technologies. Also, as I can see from the names of visitors, there are a lot of successful professionals from the data science domain, but also people from the academy. That is exactly one of the goals that this group has set, which means overcoming the gap between academia and industry. The ultimate goal we set is to engage as many people as possible to take an interest and build careers, or perhaps for some of them to innovate or start business in this area. We have assembled a strong core team to implement all plans we set, which consists of several university professors, several very successful professionals from the industry, and I think that guarantees that we will succeed. Before we start with the presentation, I invite everyone to take a part in the event by asking questions in the chat window. My colleague Alex and I will moderate it and try to answer all of them. So now we can start with the presentation. Our first lecturer and the one who is opening the chapter is Terrill Frantz, a professor at Harrisburg University of Science and Technology in the USA. He teaches different courses in quantum computing and also run the Philadelphia Harrisburg Quantum Computing Meetup group and managing Quantum Palooza. I think it's like event aggregator. Am I right, Terrill?
Yes, it's Quantum-a-Palooza.
Palooza, okay.
It takes a little while to get that out of the tongue.
Yeah. I will share the links later in the chat window. Professor Frantz will give us an overview of the current state of the quantum technologies and possible impacts of it on data science profession. Welcome, Terrill. Thanks for joining us, and we are happy to hear from you.
Well, thank you. Thank you very much. And good evening, everyone there at Quantum Serbia. I don't know if this is correct on the top of my screen there, but I gave it a shot. But I'd like to give you a warm greetings from Harrisburg, Pennsylvania, from Harrisburg University in particular. Just quickly, by way of introduction, I'm physically in the state of Pennsylvania. If this is the United States, we're up here, and Harrisburg is the state capital for what we call a commonwealth. It's technically not a state, but for all intents and purposes, it's a state, one of the 50 in the United States, and I'm right here. And to give you an idea, it's particularly warm today. It's 60 degrees and sunny here in Harrisburg, which is kind of warm for this time of year. But anyway, greetings to all of you, and thank you very much for having me. I'm really honored that this is the first meetup that you've held, and I wish you success in many, many more. As mentioned before, I run a meetup group here in the United States. In fact, I run several meetup groups around the world, actually, but the Philadelphia meetup group, we've had roughly 70 events in the past, let's say 9 months or so, 8 months. So we're quite active. We'll probably take a little rest here in the coming weeks, but I'm passionate about quantum computing. I'm rather new to the space. I've been in classical computing for around 45 years, since I was a little kid. And about 2 years ago, quantum computing found me. And for a whole number of reasons, I decided to pivot from classical computing and cybersecurity and things along that line over into quantum computing, partly because it's extremely interesting. And it's one of those technologies, unlike classical computing, that has really reached kind of a staleness to it, in my view. Quantum computing is just beginning. It's just in its infancy, and it has a lot of challenges. It's really difficult to learn, actually, at some level. And I'm just really passionate about it. Over the past 2 years, we've really been focusing in on workforce development here at our university. And just to finish the introduction, a little bit about the university itself. We're just a small school, university in Pennsylvania, obviously. We were just formed around 15 years ago and started this quantum journey about 2 years ago. And since then, we've developed courses at the PhD level, a master's program in quantum information science. We also have courses at the undergraduate level. I'm just finishing one now for this semester. And we've started teaching high school level courses in quantum as well. So getting to today, I figured this is an introductory talk today, so it's not going to be too technical unless you ask. I'd rather just start to develop some curiosity in each of you. And many of you, it seems, may have been exposed to quantum for probably a number of years already. So if you hear me saying something that you have that you disagree with, by all means, put something in the chat and we'll get the dialogue going. That's one of the fascinating and exciting things about quantum, is that no one, even those who have spent their lives working in this space, knows everything about everything. So I enjoy the opportunity to learn from you just as much as I hope you get some ideas out of what I say, out of what I give today. Anyway, it'll be pretty light. Again, I'm really focused in on trying to develop some interest in your community, in the data science community. I think quantum computing is an area that I think is going to be really important to the continued development of data science, machine learning, and AI as well. Anyway, so I'll go through a monologue on why we care about quantum technologies, the broader notion of quantum technologies, and why we're talking about it, and why the energy is starting to be put into this technology. What's the difference with quantum technologies versus other technologies that we're accustomed to, particularly in the computing space? I'll talk about some of the barriers briefly, and just a slight little recommendation on what, if I were a data science person, which I sort of am, what I recommend, what you should be doing for yourself. The first thing is a caveat that needs, I think it should be a warning that should be given in front of every quantum talk, is that particularly if you're new to this topic, I want to warn you in advance that quantum technologies are relatively complicated. And most of my frame of reference is mostly from classical computing that probably most of you are accustomed to. So relative to classical computing, quantum computing is farly more complicated. Hello world is not an easy thing to do, for example. Quantum technologies as well involve a lot more abstract thinking than we're accustomed to. Now, many of you in data analytics, perhaps, you know, you're beginning to, you know, be able to work in spaces that most other people can't work in with n-dimensional data sets. Quantum takes that quite a bit further. Moreover, and finally, you know, quantum technologies require a lot of multidisciplinary skills. And these skills have quite a steep learning curve. And so when it comes to folks in a meetup community, for example, at least relative to the meetup communities I've been involved in, many of us are you know, just non-professionals, and can get rather intimidated by the steep learning curve associated with quantum technologies, and in particular quantum computing. So this is a warning. Do not expect to be able to take an hour or two, figure out how to install Python, and maybe run a print hello world program. This is not that sort of technology. So let me get into why we care about quantum technologies. And I'm using the term quantum technologies as a very broad term, and I'll narrow it down after this into a little bit more narrow focus rather than just quantum technologies as a whole. But I'll start there. I'll start here. Why do you care? Well, you know, as an academic and lifelong learner, I come from industry before academics, but as a lifelong learner, I find it extremely fascinating and challenging because these quantum technologies are very different than what many of us are accustomed to. Now, I come from business schools and schools of computer science. I don't come from with a physics background or engineering background per se. Software engineering, yes, but it requires taking what we experience in our everyday life and forgetting about it. The ability to project to predict the trajectory of a bullet or a baseball or a football is something that we kind of are accustomed to. But quantum technologies don't involve that kind of physics, don't involve the electricity like we think of electricity or voltage, etc. Another reason I think, and this is an important reason, and it's catching a lot of attention by people, is the controversial, but the sense that we're approaching the end of Moore's law. And Moore's law is basically, you know, suggests that technology very rapidly is getting better and better and cheaper in an exponential fashion. And this has been going on for decades now, Moore's law. So we've all lived that experience where classical computing's, you know, the old adage of the phone in our pocket is multiple times more powerful than the computers that we use to go to the moon back in the 60s, et cetera. Well, Moore's law is reaching its limits. And many argue it's got a few decades to go, and I'm not disagreeing with that, but it is certainly reaching its limit. And if you think about just the practicalities of Moore's law, you know, the size of semiconductors and all those incredible electronics that the engineers have put together, they're getting down to nearly atomic size. I don't know for a fact, but I believe it's, you know, something like 100 or maybe 30 atoms wide is the width of a wire in or a connector or what have you in a semiconductor. I don't know the actual number, but eventually that will get down to 1 or 2. And when it gets down to a small number of atoms in width, you start to get into the different physics. So Moore's law is actually going to force us to start to be concerned about subatomic physics, which is what quantum is all about. Another reason you care is the demand is growing, and it's growing very rapidly. The second derivative is very large. Day by day, month by month, the speed of growth, interest, the advances in the technology and the engineering in quantum technologies are rapidly improving, and that improvement rate, the second derivative, is much faster than you can believe. I'm seeing it play out in real time here. And another reason you should care is that many of the naysayers have been saying that you know, quantum technologies, quantum computing in particular, is just a theoretic thing. We will never be able to get devices to work as we need them to. But there's plenty of evidence in the real world that argument is quickly being put to rest, in that IBM just recently announced their roadmap where they expect 1,000 qubits in 3 years or so. D-Wave computers have 5,000 qubits and so on. So quantum computers are just on the cusp of really getting out of the lab, and certainly in the coming decade, a commercial quantum computer, I think, will be quite ordinary. Already today, D-Wave, as an example, has had a commercial computer now for well over a decade. Quantum technologies, for example, MRI machines, I would call a quantum technology. We've had quantum clocks for decades, and so on. So these quantum technologies are becoming real. In fact, there's at some level of fidelity, there's some quantum technology in some phones in the coming year or two. And I think 1 or 2 phone companies have implemented some quantum technologies in their phones. So it's becoming real. Another reason you should care, this is a terrific opportunity to really compete, to really give you a competitive edge and give you a competitive advantage in practically every space that you're working in. So if you're a data analyst, you're dealing with large amounts of data. If you're working in machine learning, certainly we expect that quantum technologies will help out in machine learning as well as AI. Anyway, from a personal or from a corporate sense, now's the time to start preparing yourself and become familiar with these technologies, because they're coming and they have a long learning curve. So many competitors, and we have a program at Harrisburg University, a master's degree in data analytics, and there's not one student in a program of 1,000 students that has taken a quantum course, at least at our university yet. So as I say to the students there, if I were you, I would take a course or two, because when you go out on the job market, in the case of a student, you want to set yourself apart from those that you're competing with for those jobs, those job interviews, and certainly having some quantum background will separate you from that. And the same holds true with laboratories, universities. Right now, there are only 21 announced master's degree programs involving quantum technologies in the world. So just 21. So if you want to bring your university up to speed and compete with others around the world, the space is still small, and you can make a difference. So it does, and that's one of the reasons I brought quantum to Harrisburg University, really because it kind of sets you apart from the others if you can pull it off. So from a business perspective, many of the forward-looking companies are starting to get on the bandwagon now. They're starting to invest, albeit just small investments, maybe 1 or 2 employees in a 1,000 or 2,000 or even a 10,000 employee firm, but investing and getting involved in it at the rate of 1 or 2 FTEs is probably a good thing right now. So you're positioning yourself to compete in the future. And finally, another reason you should care, and this is really another one of my primary reasons for believing that the future is going to be bright in this space as a place for activity. The technology space aspect of it, of course, is there's a lot of work to be done there, a lot of engineering to be done. But the fact, as I see it, that there is just in the very early stages a governmental, nation state competition going on, and it's much like the race to the moon back in the 1960s. And that is when the United States was competing against the Soviet Union to get a man on the moon and return them safely to Earth. The reason for that was more political than technological, frankly. And that's what's shaping up right now between the United States, in particular, between the United States and China. Other countries or groups of countries are being involved in this race: the UK, the EU, Australia, India. But what I see happening here is the amount of interest at the nation state level, and therefore the amount of money that is going to be put into these quantum technologies, at least for the foreseeable future, over the next decade or two, will ramp up increasingly fast. There's already a bit of a one-upsmanship going on between the United States and China on investment. India's gotten in the game, et cetera. So the point is, why should you care? Is there's going to be a tremendous amount of nation state money being put into this, and that means that all of us, academics, industry, and others will find a lot of work to do here. So just bouncing back to Moore's law, here's just a graphic. I didn't want to put the graphics and the text on the same page, so I'll remind you. So this is what I'm referring to with Moore's law. You know, we're really kind of getting into stagnation. Might be too strong of a word, with all due respect to the classical computing folks, but it is definitely, we're not making technological strides like we have been since I was a kid and before. Getting to the space race type of notion, the race to the moon. This is a chart put together by McKinsey on nations' investment in the quantum efforts in the technology space for quantum technologies. This is You know, this is these numbers shouldn't be considered hard numbers. It's very difficult to calculate such things. But to give you an idea, this is what the national spending looks like in relative terms around the world. And the key here, I think, will be the United States versus China. And just for conversation's sake, just like in the US versus Soviet example of getting to the moon or to space more broadly, many do think that in some aspects of quantum technologies, China may be ahead of us in the West, and I include everybody in Europe and so on. In that in many parts of quantum technologies, China is believed to be a bit ahead of us. So it just adds more fuel to the argument that there is going to be some interesting competition going on. Without getting into the details just yet, but you know, certainly quantum computers are becoming more powerful rapidly as the engineering improves. The size of quantum computers, at least their capabilities, is increasing rapidly. And just quickly, a qubit, you could think of it as maybe a bit in a classical computer from a physical perspective. When we start getting into the 1,000 qubit range, what we call logical qubits, we can expect the quantum computers to start to really make a difference in our everyday world, and we're not that far away from it. I was at a presentation 2 days ago, and Cold Quanta, for example, is a hardware vendor, and they're expecting to be up to 1,000 qubits within the next 3 years, much like IBM and others. So quantum computers are becoming more powerful. They are moving out of the labs and so on at a pretty impressive rate at this point. Now, you know, why are we talking about these quantum technologies? Well, and what makes it interesting is that what we're doing with these quantum technologies, we're taking advantage of the quantum physics and the laws of quantum mechanics. Now you know, as human beings, we've been doing this for a million years. We've been taking advantage and using physics as we know it. And that's the key, as we know it. We don't experience quantum physics and the laws of quantum mechanics in our everyday world. And that's what these quantum technologies are all about. There's a whole different set of laws and rules and mechanical things going on at this atomic and subatomic particle level when it comes to physics. I'm not a physics, I'm not trained in physics. So to me, this is very interesting and very new. I trained in business and other more high level things. But there's a whole different science and world down there. You could think of it, we are land-based animals. Could you imagine if suddenly we were able to, live, breathe, and work in the ocean? It's a completely different landscape, a completely different world. And in these quantum technologies, we're working under the laws of how protons and electrons and photons work, the particles, if you will, of light, how they behave and what are their laws. They don't have the laws like we're accustomed to. There is not a very deterministic world down there. Things are quite a bit more random than we are accustomed to in our world here. So that's why we're talking about it. That's why people are excited about it, because the rules that we are working under to try to make things happen, to create computers or other devices or build networks, the rules are completely different from what we've been working with. And that's what makes it so difficult, but that's what makes it so exciting, because you're playing in a completely different game. There'll be some, I'll get into them, there'll be some roadblocks and barriers to getting things to work, but there'll be also some opportunities as well. So think of it as going from, you know, maybe playing a sport like football, and, you know, now you're involved in a sport like, let's say, I don't know, synchronized swimming. It's a completely different thing. So when I speak of quantum technologies, just to be clear, quantum technologies is a very broad term. And here is where some of the confusion starts. Quantum technologies have actually been used for decades, as I mentioned before. We have things like atomic clocks. We have MRI machines, which use quantum technology. So there's a whole area of quantum technologies that involve sensors, metrology, and imaging, for example. And you know, let me give you an example of a use case in sensors. Is, you know, submarines, which are underwater, cannot use GPS systems, as I'm told. It's incredibly challenging for a submarine to keep track of its location in the oceans. And I'm told that quantum devices will or are being applied or being researched for military purposes, so that submarines do not need to come up above water to try to correlate their location, where they think they are versus where they are. They'll be able to use, there are quantum devices being developed that will help submarines keep track of the amount of traveling, the distance a submarine has traveled, for example. Things like just temperature and just ordinary things that we measure every day. There are quantum devices being developed to measure things which far greater fidelity than we have, you know, in measuring temperature with a little bit of mercury and some glass. There's a lot of work being done and exploration being done in the area of quantum cryptography. Many of you have probably heard about, you know, quantum computers breaking RSA encryption in some of our internet key distribution techniques and such. That, by the way, is all theoretical right now. Our computers, the quantum computers, are not large enough yet to break that. But there are some special principles of quantum technologies that can actually produce impossibly to break encryption. Right now, all of our encryption in data, as you probably are aware, is based on a challenging math problem with a one-way math problem with a backdoor to it, and with using quantum technologies, we can make perfect encryption that is not dependent on math games or puzzles. It's based on quantum physics, the randomness associated with quantum physics. And there are other aspects of quantum physics that are being looked at for things like quantum communications. So there is such a thing as a quantum internet being developed, and it has particularly unique features where you could think of it as wireless and RF-less communications. So communicating without radio frequencies, for example. Won't get into it here, but the point is that we're looking at those strange physics at the quantum level and finding ways to use it for perfect cryptography and some really fascinating ways of communicating information from one place to another in a way that doesn't require wires or radio waves. So if that doesn't interest you, I don't know what will. So in particular, when it comes to data scientists, I think the two most relevant aspects of quantum technologies, the subcategories, if you will, are quantum simulation and quantum computing. Quantum simulation is an area that I'm just starting to dig into, and I think that's where I will ultimately land. The ability to do simulations, Monte Carlo type of simulations, for example, is something which I've been doing that for probably 20 years now. I've been modeling organizations and organization behavior in human organizations. And I use agent-based modeling to simulate that behavior. And because of the computing requirements of agent-based modeling and such, you know, I'm really limited as to the number of actors I can simulate in an organization. More importantly, the number of differences between actors I can toy with in a simulation. And with quantum simulation, in theory, I'll have much greater capability to represent an enormous number of states in a system. And that's just for me working with organization behavior, but probably much more importantly, the ability to simulate chemicals interacting with one another, biological systems interacting with one another, etc., are some incredible use cases, and I'll mention them a little bit later again. Now, quantum computing is the area that the meetup community is paying most attention to. It's what seems to be the most reachable by the most number of people when it comes to quantum technologies, meaning it thanks to companies like IBM making quantum computers available to the public for free. The interest in quantum computing in particular has zero cost when it comes to, you know, capital to get involved in. These others like simulation, communications, etc., you know, require equipment, but courtesy of IBM and others again, the cost to the capital required to get involved in quantum computing is essentially zero. So there's a tremendous amount, and that has spawned over the past 3 years a tremendous amount of interest by not only, you know, university researchers, which sometimes have a budget, sometimes they don't, but by the masses out there, the public, as well as companies. IBM making their quantum computer available to the public has just been an incredible catalyst in moving quantum technologies and in particular quantum computing forward. So they deserve a lot of credit to that. But this is really where I'll focus my attention to today, is on the computing aspect of it. So what are we, you know, continuing, you know, what we're talking about here? Quantum computers are commercially available. They have been in a lab for a decade or so now in small sizes, but anyone can get access to D-Wave computers, Rigetti quantum computers via AWS, Amazon's AWS service now. So anyone can plug in and start to experiment with those machines. Azure, any minute now, Microsoft Azure will take their cloud service for quantum computers out of really beta testing and make it available for anyone. That should be happening literally any day now, I would think. So we're talking about it because this stuff is real. It's still in the lab to a large degree. but there are computers that people can put their hands on figuratively and start to learn how to use these quantum computers. So that's why we're talking about it. Something to keep in mind when it comes to quantum computers and hardware, there are basically two types of quantum computing devices that you should be aware of if you're just joining us in this adventure. One is an annealing computer, an adiabatic computer, quantum computer, and the other is a gate-based quantum computer. The annealing type of computer is most often associated with the D-Wave quantum computer. Many of you may have heard of that. It's a Canadian company. They've been in production and have been producing commercial quantum computers for probably a decade now. And they should be commended. They really were on the forefront of commercializing quantum computing. They're kind of like the stepchild or the black sheep in the family of quantum computers. A lot of purists argue that the annealing type of quantum computer isn't anything to be excited about, but they are commercially available and they are solving real-world problems, not necessarily problems that a classical computer cannot quite reach yet. I would give it another year or two, and then we should pass the capabilities of classical computers if you're interested in annealing, in particular, optimization type of problems. The gate-based quantum computer is by far the most talked about, the most widely being investigated type of computer. And that's what I'll cover a little bit later today. When it comes to the gate models, there are lots of different modalities. There's lots of different ways to engineer a gate-based quantum computer. Things like ion traps and all kinds of modalities. You could use electrons, you can use atoms. The list goes on. There's 5 or 6 candidates that companies like IBM, Google, and so on are working towards. The jury is still out on which of these 5 or 6 or 7 modalities on hardware side will come to fruition. The people that know hardware the best are saying that, you know, they expect there'll be probably a world of 2 or 3 different types of quantum computers available as things mature, because each of these different modalities, the way of doing the hardware, have particular advantages and disadvantages. So there's a lot of work being done on the hardware side. The jury's out as to which are the best, and we don't know how that will shake out yet. And there are a lot of big name players. You know, Amazon, Baidu, Alibaba, Google, Honeywell, the list is just growing. Intel, Toshiba, there are dozens of big name players out there developing hardware primarily. In the startup space, there are startups out there. IonQ, for example, is starting to really make moves in their hardware, but there's dozens and dozens or scores of startups in particular on the software and algorithm space working on developing the quantum computing capabilities. Some of the applications, and this is where, you know, really, this is where the money really, what the money really cares about. There's a tremendous amount of work being done on machine learning applications because of the parallelism-like features of a quantum computer. A lot of researchers are working on algorithms that We don't know for sure if a quantum computer will benefit the machine learning community, but I'll tell you this, there are a lot of companies out there and a lot of people, universities, working hard on quantum machine learning, QML, algorithms and techniques. There are companies, Goldman Sachs, JP Morgan, and many of the financial firms, Wells Fargo. They have entire teams working on quantum algorithms in the financial services space. Certainly, you know, when you get into simulation, the weather forecasting, the big win might be in biomedical world. We have things like personalized medicine becoming possible, etc. Now, when it comes to the machine, for this audience here, I'll say this, you know, when it comes to machine learning, I don't think anyone's really developed an algorithm that has to surpass a classical computer just yet. The hardware is not there yet, and I don't think the techniques are there yet. There's a few fundamental problems we can get to later on, making things particularly difficult when it comes to machine learning, namely the ability to store data in a quantum computer is a practical impossibility. But that is an area that I think this community should delve into. What are some of the differences? Now, going up the stack, if I may, as a developer, as a problem solver, computer programmer, or circuit designer for a quantum algorithm, there are some particular features such as entanglement, superposition, wave-particle duality, the uncertainty principles, the ability to tunnel. These are features, these are such features, and I'm not going to explain them all here. I'll go into one or two a little bit to give you an idea, but these are the physical quantum mechanical concepts that we don't experience in our everyday world in Newtonian physics. Most important for you to know if you're going to be interested in this technology is this notion of decoherence. So unlike my laptop, which I can plug on and hopefully it'll run forever, quantum computations generally happen in less than a second. The underlying physics, don't last very long. So it's not like you turn on an algorithm and let it run overnight. Your algorithms basically run short of a second. And so it's decoherence. So the qubits, if you will, the bits in our quantum computers last an incredibly short amount of time. So that's an interesting challenge. And there's a tremendous amount of environmental sensitivity in the quantum space, and that is electrons are for example, are affected by their environment. So things like light affects a proton or an electron, temperature, heat, anything like that will affect an electron, for example, that you are trying to control as a developer, as a software person. You're trying to control a subatomic particle, and that subatomic particle is constantly being affected by its environment. So you basically have to get down to near absolute zero temperatures to slow down the movement and the environment that these bits, or these qubits as we call them, operate in. So it's extremely difficult challenge engineering wise. So I'm noticing the time here. Let me get into some of the more gory details. I'll go by rather quickly. I wasn't planning to turn you into quantum computing experts in this first go. Again, I'm just trying to generate some curiosity and some interest in you if you don't have it already. But one of the first things to appreciate when you're dealing with a quantum computer at the software level, if you want to think of it that way, is that we're talking in, when in a classical computer, we're talking about bits, and most of us are familiar with the notion of an on-off state, where a laptop bit is either on or off. In the quantum space, we have what are called qubits. And a qubit is a entity that can have any value that you could imagine in the complex numbering space. But in short, we have a on and off state, but as this sphere here indicates, if you think about this sphere and we have a tensor, an arrow, let's say, that originates in the center of the sphere, we can move this arrow or this tensor around in this space here. That basically can represent any number that you care to think about. So this really has an unlimited state space, whereas a classical bit is either on or off. So if you think about that for a bit, no pun intended, that's pretty fascinating. It's one high school level example I give, in your laptop, if you want to represent the number 1.25 euros, that takes 64 bits, at least in a laptop. Whereas 1.25 will only take 1 qubit. Or if you want to represent, the number pi, you could represent the value of pi in a qubit. Whereas a classical bit, you're going to have a limitation there, even if you use scientific notation. So this is a fundamental difference between a classical bit and a quantum qubit. And this is why, we do get excited about a quantum computer that has 100 qubits to it, because we can represent an incredibly large state space with a qubit. Another difference that is something to pay attention to, most of you will have to learn the complex or imaginary numbering systems, imaginary numbers. Think back somewhere along the line, you learned about I, which is the square root of -1. We work in this complex numbering space all the time in quantum computing. Now anybody who knows complex numbers knows, they're really not that difficult. But if you don't know much about complex numbers, or you haven't been exposed to I, it's pretty intimidating up front. But if you think about that, we only deal with the real numbers, sorta, in classical computers. If you deal with complex numbers, now you've got an entire another dimension of values to work in. If you're going to be working in quantum computing, you're going to need to bone up on your trigonometry. Shouldn't be that big of a deal if you've had some training along the way, but when it comes to folks learning quantum computing on their own, they get tripped up with the trigonometry because they may never have really used it before. So we use trig functions, sine, cosine, etc. When we refer to this tensor here, we're referring to the degrees, its position in this sphere. And so we need to be using trig functions quite a bit. Another real important thing that you need to be aware of, these qubits, when you measure them, you lose the state. So I think of it as a coin flip. So a qubit is a coin that is flipping in the air, and you're basically manipulating that coin in the air so that when it finally comes down to the ground and lands, it it ends up as either heads or tails according to what you want it to do. So a quantum qubit is very similar. When you measure it, you get either a heads or tails, or a 1 or a 0 in value. You cannot measure a qubit and get its current state. It's a probabilistic thing, whether it's a 0 or 1, just like that coin flipping in the air. So when you look at that tensor, where it is in that sphere, it's called a block sphere. That position of that arrow in that block sphere determines the probabilities of a 0 or a 1 coming up. So for example, here in this block sphere here, if the arrow is if the tensor is pointing due north, for example, in X, Y, Z coordinates, and you measure it, you get a 0. If it's pointing down here, you'll get a 1. If the tensor is pointing over here, let's say, you have a 50% probability when measured that it'll be a 1, and you have a 50% probability when measured it'll be a 0. Now, if you move the tensor here, for example, you have a 75% probability that when measured, this will go to a 0, and a 25% probability when measured, it will go to a 1. So this gives you a flavor. I'm not going to talk about a lot of details here, but it gives you a flavor of some of the challenges when you're working on quantum computing algorithms. You got a completely different world than what we're accustomed to in classical computing, which is let x equal 1 plus 2 or something like that. This is a very probabilistic world that we're working in. So to program a quantum computer, we're basically taking this tensor and we're moving it around in this block sphere effectively, so that when measured, we'll get the correct result. Let me just take 2 more minutes here, and I guess we'll open up for questions. I got a few more things here to go over, but I want to just give you an example of what I'm talking about here. So if this is a qubit, for example, and here the tensor's here, it's at state 0. Now, if I set the tensor to, if I move it down to the bottom here, to the south pole, if you will, when I measure it, it will be a 1 for sure. It's 100% guaranteed to be a 1. Now, if I move the, let me just set it to 0. If I move the tensor to here and I measure it, it's got a 50% probability. Here's the probability of 0. Here's the probability of 1 and the probability of 0. Here, it's a 50-50 probability. If I move that around a little bit, you'll see the probability changes slightly here in this case. If I move it here, I'm moving the probability around. Here, it'll stay the same because I'm moving it around different axes on the ball, on the sphere. But essentially, that's the game we're playing. Moving this tensor around so that when we measure it, it gives us a 0 or 1. There's a lot more to it. We have what are called circuits instead of programs per se. So here, each one of these lines here, this is a simulator that's available online. Each one of these lines is a separate qubit. So here, if I put what's called a Hadamard gate, just like in classical computings, we have AND gates, NOR gates, NOT gates, etc. In quantum computing, we have something similar. This is called a Hadamard gate. And the Hadamard gate takes a state 0 tensor, so it's pointing due north, and basically moves it to this point here on the equator. Let's see if I can get that set. It moves it here, so it's 50-50. So here, you'll see in this simulator, it's at 50%. And if I pull another Hadamard gate down here, etc., you'll see that this is 50%. So to give you an idea of what a circuit, we call them circuits, looks like, we have these qubits here, and then we apply these gates, which are matrices. We apply these matrices to these states and come up with new states, etc. So there's a lot more to it. Let me get back to the slides quickly, and then we'll open up for any comments or questions. So what are the barriers quickly? The problem is with this technology, errors, as I mentioned before, with decoherence and noise caused by the environment, and the ability to control the subatomic particle is still creating a lot of errors. The IBM machine, for example, has a very high error rate, whereas the IonQ machine, which is a startup company, which has a different hardware modality, has a much better error rate, but it's far slower in how it responds to the gates, etc. The decoherence is a huge problem. We're working on how to extend the life of qubits so that they don't disappear in a flash. And probably one of the biggest barriers, mostly on the social side, is the uncertainty of the technology. We don't know for sure if these quantum computers in particular will actually be better than the supercomputers we have today. We're not sure about it. Let me just end. And so those are the big challenges coming up here. What a data scientist should be doing, in my opinion, is starting to learn about this stuff. And in particular, YouTube and meetups around the world are having probably 1 or 2 quantum machine learning events, certainly 4 or 5 per month, that I encourage you to delve into. They'll talk about, support vector machines and all that goodness. One of the problems specific to machine learning is the decoherence problem. There's really not a thing such as quantum memory right now in the way we think of it. So that is a big barrier to machine learning. But using hybrid techniques where we're going between classical computing and quantum computing, a lot of people think there'll be some dividends coming from the quantum computer. So let me just end here. I know that was kind of hand wavy. I tried my best to get a little bit of whet your appetite when it comes to the challenge of and excitement and oddity of programming a quantum computer. But let me just stop here and open it up for any questions, whatever you'd like. I have the URL for Quantumapalooza on the screen there. I encourage you to take a look at that site. What it is, it's a site where I maintain free quantum online events going on around the world. There are roughly 3.6 events per day, every day of the week. So there's plenty of ways to learn about quantum computing, and in particular machine learning and such, which may be your primary interest. So let me end there. I apologize for the lengthy monologue, but I hope that was informative for some of you, if not most of you. Any questions?
First of all, thank you, Terry, for your wonderful presentation. For me personally, it was very inspiring, and I think that you managed to, let's say, fire up the public, because we have a lot of questions. So we will start with the questions without any further hesitation.
Cool.
So I will just read it in the line that we got the question. So first of all, it's very easy question, I think, and it's about Harrisburg University, and the question is, does Harrisburg offer online masters in quantum computing? This was asked by Asha.
Yeah, I'm developing the marketing materials for that. Thanks for asking, by the way. The master's program is a hybrid program in that the quantum parts will be completely online, available to people around the world. And I'm working on that now so that you could take the 6 quantum courses online and then get a certificate in quantum, QIS. And then if you choose, you can work out finishing a complete master's degree that might require coming to the United States once or twice. I'm not sure. So it's kind of a hybrid answer there. For the quantum parts, they are online.
Okay. Thank you for
and you get college credit.
We also have one question from one person who started this this meetup, and that is, if you make a parallel between classical and quantum computing, in which year or decade we are at the moment? Is it 50s or maybe 60s or something else?
40s.
Okay.
We're still at the vacuum tube stage.
Okay, this is interesting answer. I didn't.
But that's an opportunity. I'm thinking back to ENIAC. You know, the famous pictures of 3 or 4 people in a room. You know, that sort of thing. You know, but we're getting to the 50s very quickly.
Okay, nice. Okay, the next question.
But let me add, what's fascinating, what I think is really cool, is that the trajectory of classical computing basically went from hardware to, why don't we create software? Why don't we create a machine language so that we don't have to move the wires around? And then, let's make an assembler. Why don't we just start creating some high-level languages like Fortran and such? And then you get into 5GL languages, et cetera, et cetera. So as I see it, it was pretty much a sequential development. What's really fascinating in quantum is that the various aspects, the various levels of the stack are all being developed at the same time. So instead of, figuring out, vacuum tubes and all that goodness, and then going to software and, now we can even network these things. We want to get them together. We're working on the hardware. We're working on the machine level assembly language stuff. We're working on the higher level languages, and we're working on networking all at the same time. And it's this really neat dynamic from a social scientist perspective of we're all making bets on each other, because if the engineers don't get these machines to work, the software people just have to go away. And if the software people don't create algorithms that really take advantage of the hardware, it doesn't matter. So it's a real fascinating thing to see all of them, and we're all kind of jockeying, like watching what the others are doing.
So basically,
very, very different.
Yeah, like we can sum up. We can say that basically we are making a lot of progress in every parallel direction. So we can make like, let's say 50s or 60 much faster.
Yeah, the development's being done in parallel rather than sequential. So the speed is much faster. Like the machine learning people are working on algorithms, for machines that don't exist yet. But 3 years from now, they may be there, and boom, they plug them in, and hopefully they'll run.
Okay, this is interesting answer. Also, we have one, let's say, technical topic, and it's at the moment, the focus is on hardware development. Qubits are being recounted. There is an ongoing race for the quantum supremacy. But on the other hand, how important is for us to work at the same time on developing quantum algorithms, and how much they can improve or impact the whole industry? Basically, if we can reshape, what is your experience, and what do you know about progress in the field of quantum algorithms?
Like I said, that was a perfect question. They're all moving in parallel. I don't know how to explain it, but there's significant progress being made. Just in things like portfolio optimization in the stock market and such, 60 some odd stocks at one time now running on quantum computers. Now that could still be done almost, with a supercomputer, you could still optimize a portfolio of 60 products, instruments. But, that's at the edge of the most powerful supercomputers now. And that's being done on D-Wave computers right now. So, we won't know whether the machine learning people, for example, the quantum machine learning people, we won't know for sure if their algorithms work until we have the hardware to actually do it. A lot of things in theory don't work in practice. Just like Shor's algorithm, which is widely known, it's a quantum algorithm, and that's you know, that's a huge catalyst to the industry. I mean, that factors numbers. It does prime factorization on a number, and the largest number I think to date is, you know, in the 70s or maybe 100 that we've been able to factor. It's like trivial.
Okay.
But in theory, you know, when we get 1,000 machines, you'll be able to break, you know, RSA encryption at 1,000 qubits. So a lot of progress is being done, but we don't know for sure if it's real progress until we can actually run it and do it. But, you know, that will happen fast. That's the thing. It's not sequential. It's all in parallel.
Okay.
So, you know, a month after, you know, we get a 2,000 qubit quantum computer, you know, we'll be breaking RSA encryption like in 30 days because all the work's been done.
Okay.
That's why you have to prepare now.
Totally understandable. And also, if you didn't, if somebody of you that didn't see, Sasha has excellent remark that there are different kind of quantum safe algorithms. Some existing encryption algorithms are relatively safe, which is not the case with RSA. Some of these new algorithms rely on symmetric keys. This is the case where a function will produce two symmetric results from one single input. It is very difficult to reverse engineer the input. So some functions include randomness to produce outputs, but the standardization organizations are still working on selecting really quantum safe protocols. You can check the ITU, for example. They have launched several working groups to agree on this new standard. So this was the comment also from Sasha, and it was totally combined with what you said. And one additional question regarding algorithms is, what are the key features of quantum resistance algorithms which make them resistant to quantum computers?
So post-quantum cryptography is being shepherded by NIST, the National Institute of Standards and Technology in the United States. They have a competition going on. There are 7 final candidates right now. There's one basic type that looks to be, they tell me, is the most promising, and it's one based on vectors, where or lattices rather. I'm sorry. So think of a three-dimensional shape that has integers, that is integers, based on integers. Okay, so it's a bunch of dots in a lattice, right? And you play around with the vectors in those lattices, and you change the basis of the lattices, and so you try to guess the closest basis to a point. Anyway, they're called lattice-based techniques. YouTube has a few good videos on them, but they're still mathematical problems, and at this point, no one is believed to know how to break those kind of problems with a quantum computer algorithm. Okay. But their lattice-based are the most likely winner. In 2023 they'll come out with that. And keep in mind, so what is of concern here is the key exchange that goes on. So the symmetric key cryptography that goes on most of the exchange of data, that, you know, with AES techniques, that will stay. It's the key exchange at the beginning of a protocol between two computers that is what will be changed. RSA is where you and I, as a client or two clients, share the keys. We need to figure out how to get a shared key. And that exchange there is the RSA exchange. It's that initial setup is what is RSA and which can be broken.
Okay. We have like a few set of questions that I would like three set of questions I would like very quickly to ask you. First, because you're on Thanksgiving, so I think that you would like to come back with your family to spend the time. So one is two are technical. One is a bit let's say oriented toward the application and career. And we will start first with technical. What is a technical approach to retrieving info from superpositioned states or parallel computation when it means collapsing quantum state to a single measurable, the most probable one most of the time? So the question is, what is the technical approach to retrieving info from superposition states or parallel computation? And what does it mean collapsing quantum state to a single measurable?
So yeah, we don't have QRAM right now.
Okay.
But there's, I hope this is a reasonable answer. It's called super dense encoding. And so you've got that qubit there. And remember I said you could represent a number by in a state in that qubit by moving the tensor around. Well, you can take that qubit and kind of break it out into lots of different logical states. So with one qubit, like imagine you needed to keep track of a 4-bit value, 1101, let's say. Well, you can represent those 4 bits in that one qubit just by thinking about it as the number 1011 or something, or whatever. Okay. So it's called super dense encoding. Right, so that's the best we've got. So you can put a lot of data into a single qubit, but the fact is it decoheres very quickly. And that's what people are trying to figure out. That's what the machine learning people have the biggest problem with is, you know, you're processing lots of data, right? And quantum computers are not about storing data. Quantum computers can't even add, for goodness sakes.
Okay.
It's true.
So basically, okay, we will now switch to one non-technical, and that is, it has a 2-part. First one, from the current position, which field can benefit mostly from the quantum computing?
Biology. You know, the chemical compounds and stuff. So what a quantum computer is especially uniquely suited for is representing, you know, think of it as a network, right? A social network, right? You could, where the expensive part is keeping track of the number of relationships between all the nodes in a network. And so, like, I'm not a chemist, but I think that's how chemistry works. You have a compound or something and it has a relationship with other compounds. And right now there's a limited number of relationships that they can simulate. With a quantum computer, that number of relationships basically goes to infinity. And so they could actually, you know, do computer modeling of the COVID virus perfectly because you're not limited to the number of relationships, you know, that little compound has. That, you know, that's the real exciting part, in my opinion, of quantum computing. It's not really that it might be a little bit faster or a lot faster in some cases than a classical computer, but the state space is so much greater. You know, a single quantum computer, you'll be able to represent every grain of sand in the world, for example.
Okay.
Which is a ridiculously large number, but because of the way nature handles that, we can represent that state. So that's why I think biology and chemistry and all that, weather prediction, the same thing. You'll be able to put like the weather for the globe into a quantum computer.
Yeah, basically this was also like we had recently at the conference Bob Sutter speaking, and he basically gave the same answer as you, that he believed.
Oh, good.
Yeah, basically when you said biology, and by that you mean basically I think that there is a let's say there is a alignment between people who are inside the quantum ecosystem, which can be the first thing. And I think personally I see it very.
I learned a lot from Bob Suter too. But yeah, so that's to me, that's the main thing, is the number of states you'll be able to represent. That means I could, in my quantum computer simulation, I could have an agent node in my simulation for every human on Earth.
Yeah,
and their children.
That sounds a bit, let's say, a bit creepy, to be.
Well, the hard part, the hard part would be getting that data. So you still need to model the data,
of course.
but actually that's not getting so hard now, right? If you take Facebook and you take WeChat from China or whatever, and you put them together, you got 95% of the world, right?
Yeah.
So it's not as far as we think.
Okay. One additional question regarding like the soft question. Let's say it's, in your opinion, what is the best research discipline for young researcher to enter the field of quantum computation and quantum technologies?
Well, first of all, that's a great question, because I'm starting to morph into a slightly different answer to that. I think the thing we got to be careful of is a quantum computer is much like a GPU in a classical computer, a graphical processing unit. It's for very specialized purposes. And just like a GPU is generally very specialized for, displaying on a screen, images on a screen, and some very sophisticated computations. And, you could use a GPU very easily because the software makes it real easy now, right? The answer to that question is, I think you want to develop an understanding of quantum computing, but by far the more important thing is understanding the application that you're going to be working in. So you want to learn the technology, but understanding the algorithm or the application is 100 times more important.
Okay.
And that's the hard part, because you're going to, to use it to its advantage, to what it's best at, you really need to understand chemistry, for example, or you really need to understand machine learning or artificial intelligence. And that I think is going to be the bigger challenge.
Yeah, basically, I think that we can put very, very strong parallel with the data science there, because also, if you would like to be a data scientist, your domain expertise and knowledge is very important, because you need to understand what does it and how does something work. So basically, I think that there can be a great parallel between aspiring data scientist and aspiring quantum computer or quantum scientist. So basically, also I would like to add, Sasha was very active with RH, and thank you, Sasha, for that. So he also had his opinion about this previous question, and basically he said that concerning the research topic, it depends on your background. If you're in quantum physics, experimental work on new hardware can be the best option now. Electrical engineers can focus on the engineering aspects, cooling equipment for superconducting qubits or control equipment, for example. Computer scientists can focus on quantum algorithms. Quantum chemistry is also a very interesting area, as we may see that everyone is saying about quantum chemistry. And basically, what we can do inside of it, we can theoretically develop new techniques to map, for example, fermionic Hamiltonians to qubits. So basically, also I just wanted to add what Sasha said. And
that's a great answer, actually, Sasha, because I mean, you're right. Buried in my response is a bunch of assumptions. It depends. Are you trying to be productive tomorrow? If you want to get hired and work in this space tomorrow, being an engineer is the way to go. If you want to be, it depends, really.
Yeah,
and that's a good articulation of it.
Well, I have noticed actually that there is a lot of investment, and as you have mentioned in the beginning of your presentation, quite a strong race between different countries, regions, and corporations in who is going really to develop and produce better computer. And as there are several competing technologies, well, that is the very fertile ground for research topics and for interesting projects. And that is actually what is a bottleneck currently for the further development of quantum computing. So for those who are in quantum physics or in theoretical physics, I think it's very logical, and it can be very good to develop the career in that hardware development field. But of course, I mean, it's not only that hardware domain that is developing. So you have just mentioned that this the interlock between the practical domains, between the industry, the applied algorithms, and what the quantum computing can offer is also very important, because you need to understand exactly on one side how these quantum algorithms work, the other side, what are the most complex problems that cannot be resolved now with the classical computation, and how they eventually can be deployed or implemented with quantum computers. And that is also very difficult area. So those who know, I mean, as you have, I agree totally with you, as you have mentioned, that those who understand those disciplines exactly what are the most difficult problems, they will be able actually to benefit maybe the most when we have more advanced computers.
Yeah, I mean, you know, it's really, there's a tremendous amount of opportunity in every aspect. And it's really, I think, you know, which drives an individual the most. You know, is he or she an engineer? Do you like that kind of stuff? Do you like algorithms? Or do you just like biology? If you love biology, learn some quantum, because it'll, you know, you can start to grow plants in a computer. Yeah, but yeah, there's so much opportunity. That's what's tremendous about it.
Yeah, sounds very interesting to be honest about building. Okay, and the last question, but not the less important, and it was from while you were presenting the sphere and the complex representation and E number, and there was a question: what can you say about the states in the sphere? If you can relate to which part of your presentation I'm pointing toward. It was like now previously.
So
I think it was 14th, I think.
Oh, got a slider?
A little bit. No, it was here, yeah.
Okay. So so the state is the position of the tensor in the sphere. And it's got 3 axes. And you know, think of it as 3 coordinates. And that's the state. And when you measure that state, it always comes out to 0 or a 1. So it's like, it is a black box. You literally can't figure out the state. You'll never know the state. You can you know, you can move it to a particular state, but if you just gave me a qubit, I would not know. I would like, if you created a qubit, you put it into a state and gave it to me, I will never know that state. I will only know either 0 or 1. It's a constraint of the physics.
Okay. So
you know, unlike in a classical computer, right? I go to RAM and read it, and it doesn't change. But here in quantum, when I read it, it changes. Hey, I didn't make up the science, man. And, you know, a much greater being made that up than any of us. But that's one of the characteristics of the science down there, and that's either a problem or an opportunity. It's up to you.
Okay, it sounds very interesting. Also,
because not knowing that state is an opportunity if I'm communicating with another computer and I got, you know, somebody tapping into the communications. If someone reads that qubit in transit, I will know it. That's why we have quantum communications, is because if you have a listener on that communications, you will know when you're being eavesdropped on. Unlike today, right? I can intercept your internet communications and you would never know it.
Yeah. Okay. So basically,
Yes.
I think that this was the last question that we got.
Okay.
Terrill, I would like personally to thank you because for your very detailed and very excellent presentation. It was
Thanks.
very pleasant to listen to you, how you explained the basics and the fundamentals of the data science of the quantum computing, and how it can be also in one part what data science can do. Also, thank you for your answering to the questions. Like I said, we had a lot of questions. Usually, we don't have this much questions, so I think that the people in the public attendees were very excited and very motivated for this lecture. So once again, I would like to thank in front of Quantum Serbia initiative and also Data Science Serbia, and for sure, like for everyone else, we will keep in touch. Soon we'll have one additional meetup, which our speakers will be Marina Radulashki and Ognjen Markovic, who are US researchers from Serbia, and they are doing their research in part of quantum computing. So you can, and quantum and in general, so you can also hear their stories, how they start their career, and what they can say as somebody who traveled from Serbia to US to be part of a quantum ecosystem there. So thank you all, and we will keep in touch.
My pleasure. And
yes, if I may add,
yeah. Okay.
my pleasure. And I'll make sure that I get your meetups on Quantumapalooza so everybody can drop in. Thanks.
Okay. Ilya?
thanks. Yeah, I also want to thank Terrill and to invite all participants to join us in the future events. And also, since we are still at the very beginning, if anyone wants to take an active role in the community and help us in building it, feel free to contact us and join us. So thanks everyone, and good night.
Have a good one. Bye-bye. Thank you.
Bye-bye.